This one's going to be a little weird. In this video, I will be going over a three-component construction for an alternative number system, somewhat similar to the split complex numbers. It does some really neat stuff and will wind up revealing some surprising things about these types of systems, but as a primer for the kind of weird way one goes about thinking through such things, I'd recommend reading through the Wikipedia page for the split complex numbers before watching this. Also, maybe familiarize yourself with the power series derivation of Euler's formula. That'll come in handy too. So, okay, what is this thing? Well, first recall the ordinary complex numbers. These are formed when one supposes some value I, which we call imaginary, and which is defined such that I squared equals -1. The complex numbers may be written a plus bi, where a and b are each real numbers. Their addition looks like this, and to multiply them, we expand the terms as we would a polynomial, utilizing the definition of I when we hit the term that multiplies it by itself. Now that that's clear enough, recall the split complex numbers. In the same way that one supposes the imaginary I in the complex numbers, we define an imaginary j in the split complex numbers such that j squared equals 1. Don't worry, we'll get to the motivations behind this seemingly arbitrary decision in a moment. In the meantime, a split complex number may be written a plus bj, same as before. Addition looks about the same, and multiplication looks like this through largely the same thought process. All that said, the construction we'll be examining today is similar to the previous two, except that I'll be introducing two imaginary components rather than just one. For the sake of consistency with my notes, I'll be referring to these as I and j, though these are not the I and j of the previous constructions, and I'll make sure to clarify which one I'm referring to at all points. Counting the real component, this system will contain three components, and as such, I'll be referring to it as the triplex numbers. I and j are defined such that I squared equals j squared equals I, and ij equals 1. Another way to write this would be that I squared equals j and I to the third equals 1, since I to the third equals I times I squared equals ij, and j squared equals I squared squared equals I to the fourth equals I times I to the third equals I times 1. Yeesh. Since ij equals 1, a name more consistent with the scheme of complex and split complex may be to call these the split triplex numbers, but that's a bit of a mouthful, so I won't be using the term today. Like the previous two, addition is pretty straightforward, and multiplication can be handled with a big old trinomial expansion, followed by an evaluation of terms based on the rule we've already defined. This is the basic definition of the system we'll be examining. Now, back during the definition of the split complex numbers, something may have occurred to you. If the split complex j is just something like the square root of 1, doesn't that just make it 1? Or couldn't it also be -1? Point is, the split complex numbers don't seem to really be extending the real numbers in the same way the normal complex numbers do. Like, j squared equals 1. Why would we be allowed to do that? The instinct here, I think, is to try and quote-unquote solve for the imaginary value. This instinct doesn't come up for the normal complex numbers, as there's no real value, which is -1 squared. However, there are two real numbers whose squares equal 1, so the definition of the split complex j winds up looking like a quadratic equation. It begs to be solved because that's what you do with quadratics. So, before moving on to the triplex numbers, let's see where this instinct takes us with the split complex numbers. However, let's not be too hasty with the way in which we solve this. We've defined addition and multiplication in the split complex numbers, but that doesn't guarantee that simply taking the square root of both sides of j squared equals 1 will be a valid action. Instead, let's try something else. Start with j. This may be written as the fraction j over 1, obviously. Next, multiply both the top and the bottom of the fraction by 1 plus j, giving j times 1 plus j over 1 plus j. Now distribute j on the top using the definition to resolve the j squared. Thus, we have 1 plus j over 1 plus j, which is obviously equal to 1. So there we go, j is equal to 1. The numbers are solved and the video's just about done. Except, let's try that again. Like before, start with j and write it j over 1. Next, instead of multiplying the top and the bottom with 1 plus j, let's do it with 1 minus j, giving j times 1 minus j over 1 minus j. Distributing the j on top gives j minus 1 over 1 minus j, and by factoring out a negative 1 on the top, we write negative 1 minus j over 1 minus j, which is clearly equal to negative 1. So, what happened there? If j can be reduced to a real number, it shouldn't be equal to both 1 and negative 1. That would imply that 1 equals negative 1, and that's the kind of thing that you only ever tend to run into when you accidentally divide by 0 or something. Actually, dividing by 0 isn't all that far from the actual mistake here. See, 1 plus j and 1 minus j aren't just some random split complex numbers, they're what you call zero divisors. To see what I mean, try multiplying them together. Expanding 1 plus j times 1 minus j gives 1 plus j minus j times 1 plus j, which equals 1 plus j minus 1, which is all equal to 0. The potential answer to this would be to assume that j equals 1 or that j equals negative 1, and note that this implies one of the factors is 0. However, as we've seen, neither of these is more valid than the other, and they can't both be true. In fact, assuming either creates an issue in the proof of the other. If j equals 1, then when we multiplied the top and bottom of the fraction by 1 minus j, we were really just introducing zeros and dividing them out, which is not a valid action. But the same can be said for our proof of j equals 1. If j equals negative 1, then we're just dividing by 0 to prove an invalid point. The split complex j is therefore not equal to 1, nor does it equal negative 1. Neither 1 plus j or 1 minus j is equal to 0, but 0 is obtained by multiplying them together. Because of the effects we've seen, we'll take the precaution that dividing by 0 divisors is just as invalid as dividing by 0 itself. With that in mind, we'll turn to the triplex numbers and see if these are issues we have to worry about. Considering that in the triplex numbers, I to the third equals 1, there are again two instincts for solving this. The first is to say that I is the real number 1. Simple enough. The second is to say that the triplex I is equal to the complex e to the 2 pi over 3 times I, since by Euler's identity, e to the 2 pi I equals 1. Both of these lead to trouble, though it's less obvious how. In order to demonstrate these issues, let's try to quote-unquote solve for the triplex 1 plus I plus j in the same way that we tried to solve for the split complex j earlier. First, we'll start by squaring 1 plus I plus j. Expanding this gives 1 plus I plus j plus I times 1 plus I plus j times 1 plus I plus j, which is equal to 1 plus I plus j plus I plus j plus 1 plus j plus 1 plus I. Wow. Written more simply as 3 plus 3i plus 3j. By factoring out the 3's, we notice that 1 plus I plus j squared equals 3 times 1 plus I plus j. Hence, by dividing out the 1 plus I plus j, we find it is equal to 3, which demonstrates our first guess at a solution. Next, we'll start with I plus j. This may be written as I plus j over 1. Then we will multiply the top and bottom of this fraction by I minus j, giving I plus j times I minus j over I minus j. Expanding the top gives II plus ij minus ij plus jj over I minus j, which equals j plus 1 minus I over I minus j. Since 1 minus 1 equals 0, the 1's cancel, and we're left to factor out a negative 1 and observe that I plus j is in fact equal to negative 1. This implies that 1 plus I plus j equals 0. It's pretty easy to see how the second solution shows an invalidation of the first, since it claims that 1 plus I plus j equals 0, and the solution for 1 plus I plus j over 3 required that we divide by 1 plus I plus j. However, taking into account that 1 plus I plus j was an attempt to confirm that I equals 1, it follows that j equals 1 and I minus j equals 0, which invalidates the division in the second solution. 1 plus I plus j can't be both equal to 0 and to 3, and it's starting to seem like it's equal to neither. Now note that if we multiply 1 plus I plus j by I minus j, we get I plus j plus 1 minus j minus 1 minus I, which is equal to 0. Both of these are zero divisors, and thus both demonstrations are invalid. In fact, multiplying 1 plus I plus j by any triplex a plus bi plus cj gives abc plus abci plus abcj, revealing that if the sum of the three real components of a triplex number is equal to 0, that number is a zero divisor. So, that's a lot. It seems to be the case that attempting to solve for imaginary values isn't the right way to go about things, but it's still unclear what they are. Like, in the complex numbers, the imaginary I was the square root of -1. You could get there from the real numbers, but that doesn't seem to be the case with other sets like the split complex and triplex numbers. So how does one go about visualizing such things? That's where matrix representations come in. I probably should have mentioned this earlier, but if you want a refresher on matrices, I would recommend the 4th video in 3 Blue 1 Brown's Essence of Linear Algebra series, link in the description. That said, it turns out that all of the systems we've been talking about can be represented as square matrices. For instance, take the complex number a plus bi. How would we approach this? Well, first construct a 2x2 matrix and fill it in like this, which can be written perhaps more clearly as this. This works because the first matrix is the identity matrix, and the second matrix, when squared, is -1 times the identity matrix. Thus, the matrix follows the multiplication rule of the complex numbers, and we can convert in and out of the two without losing anything. The split complex numbers also have a matrix representation, which looks like this. The matrix representation gives a pretty good way to visualize how the split complex imaginary value j actually behaves. By thinking of j as this matrix, we can see that it is neither the identity matrix nor the negative of the identity matrix, but when multiplied by itself, it forms the identity matrix. As a representation of the split complex numbers, this is arguably the one which affords the most clarity. Now, what would a matrix representation of the triplex numbers look like? Well, we have the 3 components now instead of just 2, so we'll be looking for a 3x3 matrix. Like the previous 2, it should divide up into component matrices that behave like the 3 components of any triplex number, with the first component being the identity matrix. So how do we represent I and j? Well, I times j equals 1, so the matrices should be inverses of one another. In addition, I squared equals j and j squared equals I, so each should square to the other one. The definition is pretty symmetric, so which matrix goes to which component should produce no loss in generality. All that said, the matrix representation that fits the bill looks like this. What's nice about this is that even though it's a big, long matrix thing, it still turns out to be commutative. This is because if the 2 matrices are inverses of one another, order doesn't matter. Thus, the only combinations we see are the identity matrix with the other components, which is commutative, the orders of I and j, which are inverses, and the squares of the components, which don't have any order to begin with. With these matrix representations in mind, let's jump ahead to something neat. In the complex numbers, the split complex numbers, the quaternions, the split quaternions, and so on, there's a function n that converts these into real numbers. For each, the n function is defined so that it maintains some convenient properties. First, n of 2 numbers multiplied according to their rules for such is the same as n of the one multiplied by n of the other. It's got something like distributivity over multiplication, which will actually come in handy later. Second, for any number x, there exists some x prime such that x times x prime equals n of x. We refer to x prime as the conjugate of x, and in all the sets I mentioned earlier, It simply consists of the real part of x minus the imaginary part. So, in an effort to find an n function and conjugate for our triplex numbers, let's see if this pattern extends to our construction. Let x equal a plus bi plus cj. By the pattern, we will assume that x prime equals a minus bi minus cj. If the pattern holds, then multiplying these two together shouldn't leave any stray i's or j's, since the output of an n function is always a real number. So expanding their product gives this, which equals this. This has not worked. It turns out that while a simple pattern emerges for all those systems, it only really does so because squaring each of their imaginary components outputs a real number. As such, if we want to do this, we're going to have to get a little more creative with our explorations. Luckily, we've already gone over the matrix representations. Recall the matrix representation of the complex and split complex numbers. Now take a look at their n functions. In both cases, the n function is equivalent to the determinant of the matrix representation of each. Firstly, that's amazing, and secondly, that makes complete sense. The determinant of matrices satisfies the same sort of distributivity over multiplication that we mentioned earlier, so it makes sense that it might wind up being relevant. Considering this pattern, what does the determinant of the triplex matrix look like? Well, recall that any triplex A plus Bi plus Cj may be written as this matrix. The determinant of this matrix is a to the third plus b to the third plus c to the third minus 3abc. It happens that this can also be factored, given a plus b plus c, times a squared minus bc plus c squared minus ab plus b squared minus ac. These two factors actually relate back to our zero divisors from earlier. In any set for which an n is defined, the n of a zero divisor just equals 0. The factors here relate to the two kinds of zero divisors we came across earlier. If the sum of a triplex number's coefficients is 0, the first factor is 0 and the whole thing is. Likewise, if all its components are the same, the second factor will be equal to 0, and as such the whole thing will be. Factoring this even shows us what the conjugate looks like for a triplex number. To see what I mean, consider that I to the third, j to the third, and ij are all equal to 1. As such, our n function, a to the third plus b to the third plus c to the third minus 3abc, can be written equivalently as a to the third plus bi to the third plus cj to the third minus 3a times bi times cj. It can then be factored from this form, giving a plus bi plus cj times a squared minus bi times cj plus cj squared minus a times bi plus bi squared minus a times cj, written more simply as this. Since the first factor is the original number x, the second must be the x prime such that x times x prime equals n of x. Yay! We did it! Needless to say, this definition for a conjugate isn't quite as simple as those of the other constructions. Likewise, it doesn't have some of the nicer properties some of the others do. In the complex and split complex numbers, n of any x is the same as n of the conjugate of x. In the triplex numbers, n of x prime equals n of x squared, which I don't plan on proving here. Also, in the other systems, the conjugate of x is just x. This is not the case in the triplex numbers. Consider that x times x prime equals n of x, implying that x prime equals n of x over x. Therefore, x prime prime equals n of x prime over x prime equals n of x squared over n of x over x, which is all equal to x times n of x. Thus, applying repeated conjugations just winds up multiplying in a bunch of n functions. Since the conjugate of x is not x, we say that the conjugation is not an involution, which is sad. However, using these tools tells us that the inverse of x is equal to x prime over n of x, giving us a valid system for division, which is nice. Now let's go deeper and talk about idempotent elements. An element E of a ring is called idempotent if E squared equals E. From this definition, we can subtract E squared from both sides and then factor it out. Thus, any idempotent element must also be a zero divisor. In addition, squaring the second factor gives this, demonstrating that if E is idempotent, then 1 minus E must also be idempotent. The complex numbers don't have any idempotent elements, but it turns out that the split complex numbers do. Remember the zero divisors from the split complex numbers, 1 plus j and 1 minus j? Consider that 1 plus j squared is equal to 2 plus 2j. To make up for this, we'll divide it by 2, giving 1 plus j over 2, which is idempotent. In the same way, 1 minus j over 2 is idempotent. So, are there any idempotent elements in the triplex numbers? Well, recall that we mentioned earlier that 1 plus I plus j squared equals 3 plus 3i plus 3j. Thus, it's clear that 1 plus I plus j over 3 is idempotent. There's one other idempotent triplex number. Earlier, we saw that for any idempotent E, 1 minus E must also be idempotent. As such, since 1 plus I plus j over 3 is idempotent, 1 minus 1 plus I plus j over 3 must be as well. That is, 2 minus I minus j over 3 is the other idempotent triplex number. If you read the Wikipedia page, you'll recall that the two idempotent elements of the split complex numbers form something called the diagonal basis. That is, if you let the split complex 1 plus j over 2 equal E1 and 1 minus j over 2 equal E2, then you can write any a plus bj as a plus b E1 plus a minus b E2. The diagonal basis is just another way of composing the split complex numbers, and it makes some things a whole lot easier. For instance, where n of a plus bj equals a squared minus b squared, n of a E1 plus b E2 just equals ab, which certainly looks simpler. Also, since E1 times E2 equals 0, multiplication winds up being a whole lot easier. Where a plus bj times c plus dj equals ac plus bd plus ad plus bcj, ae1 plus be2 times ce1 plus de2 equals ace1 plus bde2. Smooth. If we try to form a diagonal basis for the triplex numbers, some interesting stuff starts to happen. To start off, let E1 equal 1 plus I plus j over 3 and E2 equal 2 minus I minus j over 3. Note first that these two have exactly the same properties as their split complex counterparts. E1 squared equals E1, E2 squared equals E2, and E1 E2 equals 0. An interesting consequence of this is that E1 plus E2 squared equals E1 plus E2, which makes sense because E1 plus E2 equals 1 plus I plus j over 3 plus 2 minus I minus j over 3, which pretty clearly just equals 1. However, E2 minus E1 squared also equals E1 plus E2, but E2 minus E1 equals 1 minus 2i minus 2j over 3, which is noticeably not equal to 1. 1 minus 2i minus 2j over 3 is an element that, when squared, gives 1, despite the fact that it is neither 1 nor negative 1. As such, the triplex numbers implicitly contain a quote-unquote solution for the split complex numbers, which is actually pretty neat. With E1 and E2, we're not actually finished. The triplex numbers have 3 components, so we're going to need a third component to complete the diagonal basis. To proceed, imagine for a moment that numbers are vectors. That is, E1 and E2 would be thought of as 1, 1, 1 over 3 and 2, minus 1 over 3, respectively. These two vectors are orthogonal to each other, so we'll probably want the third component to be orthogonal to the first two. To get such a vector, we'll take the cross product of e1 and e2. Converting back to a number gives I minus j over 3. With this in mind, I'm going to let e3 equal I minus j over the square root of 3 for reasons that will become apparent in a moment. Let's see how this plays with the other two components. Because of what we know about zero divisors, we can pretty quickly see that e1 times e3 equals 0. Now let's evaluate e2 times e3. Let's start with this times this. Distributing out the top gives this, which equals this, and then this. Remove the 3's, and we get I minus j over square root 3. Thus, e2 times e3 equals e3. Curious. Now let's evaluate e3 squared. This may be written I minus j times I minus j over 3. Expanding that out gives this, then this, and finally this. Pull out the negative 1, and we're left with the fact that e3 squared equals negative e2. To underline what just happened here, consider that a e2 plus b e3 times c e2 plus d e3 evaluates to ac minus bd e2 plus ad plus bc e3. That's the multiplication rule for the normal complex numbers. The triplex numbers contain both the split complex and normal complex numbers. Spooky. One way to think about the fact that e2 and e3 behave like complex numbers is to recall that one of the quote-unquote solutions we mentioned earlier was to set triplex I equal to the complex number e to the 2 pi over 3 times I. What I didn't mention earlier is that the complex number e to the 2 pi over 3 times I equals -1 plus square root of 3i over 2. That is, the solutions for triplex I and j are these. This is why this assumption leads to the conclusion that 1 plus I plus j equals 0, though we've already seen the issues with that. However, substituting these complex expressions into the triplex e2 and e3 gives e2 equals 1 and e3 equals I. In the full triplex systems, these expressions don't really hold, but they do serve to put into perspective why e2 and e3 behave the way they do. Anywho, with these three values, we've got ourselves a diagonal basis. In the same way that any split complex number can be written in its diagonal basis, so too can we freely convert between the normal triplex basis and the diagonal triplex basis, using these conversions. They're admittedly pretty copious, but I guess that's just the price you pay for a three-part diagonal basis. Addition in this basis works pretty straightforwardly, and multiplication looks like this, which reduces the equation to 5 terms instead of 9. The n function of the diagonal basis, n of ae1 plus be2 plus ce3, equals a times b squared plus c squared. Likewise, the conjugate of such is this, which works because e1 plus e2 equals 1. Keeping all that in mind, let's move on to another problem. We've already gone over how to add, multiply, and divide triplex numbers, but how do we handle exponentiation? It's time to enter the territory of Euler's formula. Recall the way that Euler's formula is derived using power series. First, we note that for the real numbers, the exponential of x can be written as this power series, which expands out like this. Next, we note that in the complex numbers, powers of I behave predictably. We start with 1, then I, then -1, then -I, and then 1 again, repeating arbitrarily. In particular, that means that if I is raised to some even integer, the result is just -1 to the power of half that integer, and if it's raised to an odd integer, we get plus or minus I. With this in mind, we plug xi into the power series and multiply each power of I using our rule. Rearranging things, a real and imaginary component emerge, which wind up being the power series for the cosine and sine functions. Leveraging this tells us how to exponentiate complex numbers. We can also do this for the split complex numbers. Note that the cycle for j is much shorter. J to the 0 power is 1, to the first is j, and to the second is 1 again. Whether the power produces 1 or j is just a matter of whether the exponent is even or odd, respectively. We plug xj into the exponential series and simplify. After rearranging things, the real and imaginary components wind up being those which represent the hyperbolic cosine and sine functions, giving a nice sort of parallel between the two systems. So I guess this whole thing is pretty easy then. The triplex numbers are defined by some pretty simple rules, so plugging in the imaginary components to the exponential series shouldn't be too hard, right? We want to find the exponential of a plus bi plus cj, so in advance we'll turn the addition inside the function into multiplication outside the function. Now we just want to find Euler-ish formulae for our two imaginary components. As before, we'll see how each behave when raised to integer powers. For I, we start at 1, then multiply to I, then j, then back to 1. For j, it's basically the same thing, but I and j are switched. This is actually pretty convenient, since it means the formula for j will just be the same as the formula for I, but with I and j switched. Anywho, we've got our three-part cycle worked out, so we can plug the triplex xi into the power series. Simplifying and rearranging gives us these three components, and these can also be written like this. It's not immediately clear what functions these power series represent, and I don't really want to look them up, so let's just call them functions big A, big B, and big C of x. The exponential of xj is the same thing, but b and c are switched. Thus, in conclusion, the exponential of a plus bi plus cj is this, which expands to this. We've got a mess of functions which themselves are only really defined by a handful of power series. I guess I expected something cleaner since the other sets had such simple formulae. You know what? I bet this would look a whole lot nicer if I phrase it as the exponential of the diagonal basis. Alright, so let's find the exponential of ae1 plus be2 plus ce3. First, we'll isolate the parts as factors, as before. Then we'll evaluate the powers of each component. e1 to the power of 0 will be equal to 1, which is written as e1 plus e2 in the diagonal basis, as we saw before. Then its first power is e1, so is its second power, going forward to any arbitrary power. Thus, when we plug xe1 into the power series, 1 becomes e1 plus e2, and each term's power becomes e1. Separating them out just leaves us with the exponential of x times e1 plus an extra e2. Using the same logic, we find that the exponential of xe2 is the e1 plus the exponent of x times e2. Now the powers of e3. As one would expect, it follows the same pattern as the complex imaginary I, with its first few powers being e1 plus e2, e3, minus e2, minus e3, e2, and then e3 again. Plugging in xe3 then gives this, which simplifies as e1 plus cosine of x e2 plus sine of x e3. Now we'll take these back to the complete exponential. Each factor of the exponential can thus be written like so. The first two factors simplify pretty nicely, then distributing all the way gives this, which is certainly a lot easier on the eyes than what we had in the normal basis. Actually, this is written explicitly. In the normal basis, we just declared functions equal to power series, but here we have it written using only elementary functions. Not only that, but we know how to convert into and out of the diagonal basis, so we should be able to use this to write the exponential of the normal basis using this formula. Let's see. Using our conversions, we can write the exponential of a plus bi plus cj as this exponential over the diagonal basis. Using our formula, we can then write that exponential like this. Then we convert back to the normal basis, and everything gets a whole lot longer. Luckily, we can just factor an exponential of a over 3 out of everything. Then, note that the coefficients for I and j each have these trigonometric functions of the same expression in them. Using some trig identities, we can simplify both, leaving the whole expression as this. It's longer than our power series excuse, but a whole lot clearer about what's actually going on. Actually, hold on a moment. Notice that this formula gives us a closed expression for the exponential of xi. That means we've actually found the functions given by those power series. We can even graph them to see that they line up. These are the functions for big A, B, and C. Because of how cosines work, the formula actually accounts for B and C switching in the xj exponential. That means that not only have we found expressions for big A, B, and C, we've actually gotten formulas for how they behave under multiplication with one another. I don't want to undersell this, we just used diagonal basis conversions to find 3 functions that we only had power series expressions for. That's completely unexpected and kind of amazing. So, with that, I'm winding down. Let's just find a closed expression for the logarithm of any triplex number and then call it for today. We'll start in the diagonal basis this time. If the natural logarithm of ae1 plus be2 plus ce3 exists, then that means there is some triplex fe1 plus ge2 plus he3 such that the exponential of fe1 plus ge2 plus he3 equals ae1 plus be2 plus ce3. Since that exponential can be written as exponential of fe1 plus exponential of g cosine h e2 plus exponential of g sine h e3, we get a system of 3 equations to solve. A equals the exponential of f, b equals the exponential of g times cosine of h, and c equals the exponential of g times sine of h. The first one's easy enough, just take the natural log of both sides, giving f equals ln a. Then for g, we can note that b squared plus c squared must equal exponential of g squared by the Pythagorean trig identity, implying that g equals the natural log of the square root of b squared plus c squared. Finally, for f, consider that c over b must equal sine h over cosine h, which is just tan h. To invert this, we'll say that h is the arctangent of c over b, though there are some problems with this expression that deserve their own video. Thus, since we've found f, g, and h, we can say that the natural log of ae1 plus be2 plus ce3 equals ln a e1 plus ln the square root of b squared plus c squared e2 plus arctan c over b e3. To find the natural log of a plus bi plus cj, we can convert in and out of the diagonal basis and do some simplifying to get this formula. I've left a graph in the description that demonstrates that this formula gives an accurate inverse to the exponential formula we found earlier. We could have gone straight from the exponential to the logarithm without using the diagonal basis, but no, I've tried that, it works, it's not fun, would not recommend. Anyway, as a last note, with the furnace ruining my recording, between the exponential and the logarithm, we can actually find a formula for the triplex I to the power of any real number. Figure I to the x is just the exponential of x times the natural logarithm of I. It's a whole mess, but it simplifies to this, which is pretty nice, right? Yeah, that's a nice note to end on. Love ya. Goodbye.